eventually everyone will become sick. But you'd have to slow down the progress just so that you can protect the medical system. So if you want to consider that, it's really simple. You just have to differentiate the IT. It gives you the rate of change. It gives you the new infected at a given day per day. So you can use the differentiation function in Mathematica. So what I use is d function. D and the function comma t means that you're differentiating with regard to time. And I added this thing called simplify because solution becomes sometimes complicated, but then you can convert it into a one single equation, which is easier to see. And this is the answer that you get. So all you have to do is to just plot it for the 10 days. And under the condition that you're meeting 2 people per day, quite remarkably, before the second day comes, it will reach the peak of incidence. So almost 1,000 people will get sick within 2 days. And this is not a good news for the society. The medical system will collapse. This is what we are talking about for a long time now. So this is basically the idea behind the phrase flattening the curve. So if one person meets 2 people every day, and this is what happens. 1,000 population will be completely infected within 2 days, 2 or 3 days. And then what you can do is to restrict the social contact. This is called social distancing. It can be done through various measures. You can do it forcibly, or you can do it voluntarily. But nonetheless, if you decrease the number of people you meet per day, in fact, if you only just reduce your social contact down to 25% of the original, so instead of meeting 2 people per day, you meet you meet 1 person in 2 days. If you do so, C will become 0.5 per day, and you can dramatically reduce the rate of progression of the disease. So you can see that even though it will eventually saturate into the whole population in 10 days, the rate of incidence will be spread throughout. So the medical system can deal with this increase of the patients. So this is the flattening the curve idea. I welcome you to try this at home by adjusting the parameters in whatever way you like. So I uploaded the Mathematica notebook called simodel.nb, and you can find it on my2PNU. So try it at home and try to think about the implications of this. And once again, the flattening the curve is historically well established idea, and it's probably the only strategy that we have to deal with this pandemic condition. Forget the statement I just made because it's a bit more complicated because there are seasonality and recurrence and so on. But nonetheless, we have to slow down and the progression of disease. So this graph is something that you see all the time. This one in particular is coming from the CDC and adapted by Economist magazine. So without any protective measures, without any social restriction or distancing, there will be a sharp increase of incidence. And with the proactive measures of shutting down the institutions and social contact, it can actually spread, and it can save a lot of lives. And there's a really interesting historical example. So Philadelphia versus St. Louis. So what happens is that in Philadelphia, they just didn't do anything initially. So the Philadelphia had even like citywide war bond parade, and people just got together a lot. And then after that, there's, as you can see, a sharp rise of the incidence of death. Notice that we're talking about the death rate, not the amount of infectives. But as we move on to the next We will actually talk a little bit about SIR model, and R include the recovered people and also dead people, but that becomes proportional to the infectives with some time delay. So this is actually a good marker for telling you the dynamics of I, the DIDT. But I must add that to be precise, we're actually talking about DR over DT. But anyway, nonetheless, look at the right panel. So in Philadelphia, the first case occurred in September 17th, and they didn't do anything. And they even did like this parade thing. 2 weeks plus later, let's see what happens. They get to realize the seriousness of the disease, and then they start social distancing. And even so, that was too late. And you get to see a sharp peak, and the death rate peaks up to 250 deaths per number of population, which is normalized to be 100,000. But this is quite impressively comparable to the case of St. Louis. So in St. Louis, the first case was reported in October 5th, but they started social distancing in only 2 days. And with this rapid social response, what you see is the broadening of the curve. It slowed down the spread of the disease dramatically and protected society. This is a very well-known and important social lesson. And this is basically the idea of flattening the curve. I think you know the basic idea behind it, because now I hope you understand the logistic of the SI model. Of course, disease spread in 2 days is too dramatic, right? But it is possible scenario because the population is small. We're talking about small town, and you can easily guess that any small society will get contaminated quite easily. But it's sort of like a water tank. If you have a water tank, small water tank, and put a small tint of water, ink, the whole thing will become dirty quite easily. But if you have a large amount of water, it takes a longer time to contaminate the whole population. So the same thing. If you have 1,000, it takes 2 or 3 days to contaminate the whole population. But if you have 10,000, it is delayed quite a bit more. It takes now about 3 to 4 days. And if you have 100,000 people, it becomes delayed even further. So it just tells you that a larger population takes more time to spread. It is really comparable to the diffusion of the molecules.